Okay, so I can start?
Yes.
Okay. So I feel a bit of an outsider in this session because I will not talk about radar data at all, but actually focus on satellite observations and also ground-based observations of total column water vapor, and show a study on how we might relate variabilities in the water vapor field to convective initiation in Germany. So I'm part of the RealPAP project, and the idea is to exploit the large set of observations, and our contribution is the satellite data. And the satellite measurements that we are using are from passive imagers on both polar orbiting satellites and geostationary satellites. And the measurements are made in the visible near-infrared and thermal infrared part of the spectrum. And this means that precipitation is actually invisible for these kind of measurements because it's below the opaque cloud. So why are we members in a project that focuses on improving the precipitation nowcasting and the flash flood predictions? So the idea is to use novel satellite total column water vapor products combined with cloud products to support the monitoring of the pre-convective environment and convective initiation. So for that, we develop and process high precision total column water vapor fields on high spatial resolutions of up to 250 meters. And we can also have a temporal variability of the water vapor field from observations from geostationary satellite, like the Meteosat second generation and the Severi instrument. And then you have the 15-minute resolution, but lower spatial resolution. And then in a second step, you can also start monitoring convective cloud structures, look for precursors of precipitation and precipitation intensification using these geostationary satellite observations. Okay, so in this phase of the project, our approach is twofold, you could say. So first of all, we develop the retrieval, the total column water vapor retrievals for OLCI and also for MODIS, do the processing, then also collect GPS time series of total column water vapor, and also cloud products from MSG Severi, and make a matchup of these data sets and try to relate variabilities in the water vapor field, so spatial and temporal variabilities, to convective initiation. So that's the idea. And with this, having this setup, we can also mimic somewhat the observational capabilities that the future geostationary satellite, Meteosat third generation, will have with its flexible combined imager. And yeah, this will have a much higher spatial and temporal resolution compared to the Severi instrument. And then there's also the second step where we work, where we do preparations for this future water vapor retrievals from the FCI instrument. For that, we work on water vapor retrievals from MSG Severi. So despite using a different set of measurements for this, we can still use the entire setup actually and adapt that in the future for the MTG FCI instrument. Then I also use the fast forward model RTTOF to do sensitivity studies. And we also collected 1 day of test simulation data that is provided by EUMETSAT for the MTG FCI observations. Okay, so just to show an example of how OLCI 2D total column water vapor field can look like. So this is for a day in June 2016. So we have OLCI overpasses. So OLCI is on the Sentinel-3 polar orbiting satellite, which has overpasses in the morning. And we do the retrievals for clear sky pixels. So this means I cannot use the OLCI retrievals if there are too many clouds already in the morning. But here you can nicely see all the different, a large variation in the spatial structures of the water vapor field. And when you zoom in, you can also see finer small scale structures. So we already have we did several case studies for looking at small-scale structures in a water vapor field. And this is, for example, from the MIRIS instrument, which is actually so OLCI is the follow-up of the MIRIS instrument. And MIRIS had a resolution of 300 meters. And here's one example of a day in May 2008, where we had cloud streets in the eastern part of Central Europe. And then later on, these cloud streets also developed more in the center part. But in the morning, we could already see these organized convector structures in the water vapor field. And you can see this in this red box here by these alternating lines of high and low water vapor values. And also in the lines with the higher values, this is also where the cloud streets actually develop later on. Okay, so just to show that also a lot of work goes into the processing of the water vapor for OLCI and also the validation. We do that on a global scale using a large network of ground-based observations of water vapor like GNSS or Aeronet, but also we also focus on the German domain. So fortunately in Germany, we have a very dense network of GPS stations, which serve as a good reference for water vapor validation. So this is something that we're compiling into a paper. Okay, so just to give an example of also the water vapor retrieval that we're doing for Seviri. That's shown here in the rainbow color. So this is for 4 time steps during a RealPEP case study day in July 2017. So the rainbow colors are the total column water vapor values. Then the pinkish colors are the cloud water path values from the KNMI CPP data set for Seviri. And then the circles actually show the water vapor values at the GPS stations. And so if you do like a visual inspection, you can already see that Seviri is following these areas of higher and lower values for water vapor, but there are also really some problems near the cloud boundaries and also areas where we have thin cirrus clouds. So this is also something that we have to deal with correct cloud masking when we do the water vapor retrievals. Okay, so going towards the MTG observational capabilities. So what I said before, we are doing a matchup of the OLCI 2D water vapor fields with the GPS station, the time series. So I take at each GPS station a box of OLCI, and then I also store the time series of GPS, all the time steps within 3 hours after OLCI overpass. And I do the same for MSG Seviri. So there I have a 2D field and also for different time steps. And then I look at the results based on stratification by cloud type occurrence. So this is in this presentation here, all clear, cloudy convection and deep convection. So I'm actually not doing yet really the convective initiation detection, but rather looking at, okay, how does the distribution of water vapor look like for different cloudy situations? And these cloud type occurrences depend on thresholds, simple thresholds from cloud products from Seviri. And they have to be there, the clouds have to be there within 1 to 3 hours after the OLCI overpass. Okay, so this is 2 examples of describing the spatial variability within the OLCI 2D water vapor field in the form of box plots for the different cloudy situations. So on the left, we have the anomaly for the OLCI 90 percentile. So this means I take from the 2D field the 90 percentile value and divide it by a weekly climatology. And this is why I call the anomaly. And here you can already see that when you move towards convective and deep convective cases, that the distribution of these water vapor anomalies move towards higher values. Then on the right, this is also done for the coefficient of variation, which is basically the standard deviation of the field divided by the mean. But here it seems that there is, especially for deep convection, that there's not really, not such a large difference. Okay, so we can also look at the temporal variability from the GPS water vapor time series. And this is here on the left. This is done for the number of GPS time steps within this 3-hour time period that show a water vapor increase. So we see some that for the convection and deep convection cases, we have the distribution moves towards somewhat higher number of time steps. And on the right is shown the maximum 15-minute water vapor increase within the 3 hours. And also here you see a bit of difference between the distributions for the different cloudy situations. Okay, so I can actually transform these distributions into probability of convection occurrence. So now I throw in together the convection and deep convection cases, and I can look, for example, at the upper left plot where I have this 90 percentile anomaly. When I have increased values, the tendency is that the probability of convection occurrence also increases. Of course, you also have to keep in mind what the actual relative frequency of occurrence is for all the cases. So on the lower left is showing the same, but now for the maximum water vapor increase, GPS water vapor increase in this 3-hour time period, where we see some higher probability for almost no increase. So maybe this might be a misclassification, including some front type situations. And then it increases again for higher values. So I can combine these two probabilities into a 2D probability histogram, which is shown here in the upper right. And you see somewhat a tendency of if you go towards higher values, especially for OG, that you have this somewhat higher probability of convection occurrence. Okay, so this was for all the large-scale weather situations within the 3-year time period that I took. And this I'm only focusing on spring and summer months. But I can also look at large-scale weather conditions that are more specific. So for example, when we have easterly flow and anticyclonic conditions near the surface. So these are the situations where you usually have a fair weather situation in Germany, and where you might expect that local processes might dominate the development of convection. And here again are shown the different plots. So we have the box plots on the left. Again, from the upper left, anomaly for OG, and below we have the number of GPS time steps with an increase. And here the distributions for different cloudy situations already look a bit different than when you just throw them into one. But here we have the situation that we do not really have a lot of convective cases when we limit this to these kind of large-scale weather situations. So this also leads to quite jumpy probability of convection occurrences plots in the middle. And then again, we can combine, for example, these two parameters into a 2D probability histogram, like shown here, which is also kind of jumpy. Then other situation I looked at is the southwesterly flow. So this is usually when we have so a lot of storms with heavy precipitation and also occasionally some tornadoes, especially in southwestern Germany, develop under these kind of conditions. So I also wanted to have a look at this. And also here you see the movement of the distributions of water vapor towards higher values in these for these two parameters when we go towards more convective cases. Okay, so again, the probability of convection occurrence plots here and the 2D probability histograms. Okay, so I have to check the time. Okay, so these were simple, pretty simple descriptors of the variability. And So now I'm actually working on or looking into what kind of parameters I could use to have more advanced or more sophisticated descriptors of the, for example, the spatial variability. So, for example, looking at spatial autocorrelation parameters, which somehow quantify the degree of clusters, for example, that I have in my water vapor field, or looking for boundaries within the water vapor field. So one parameter that can be used is the local Morans I index, and so this is something that I'm looking into. But I cannot show any results yet. Just that, for example, just give one example. For example, here, this is again this is the MIRIS observations from May 2008, where we had the cloud streets in the eastern part. But here, for example, in this red box, we have some clusters of higher water vapor values, but instead of looking at the values themselves, I look at the anomaly. So I subtract the weekly climatology and then apply this method for getting the local Morans I value. And when you have positive values, then there's an idea of that you have a cluster of values. Okay, so I will go to the conclusions. So our approach is twofold in this project, as I said in the beginning. So we use the setup of combining all GPS and MSG Severi to investigate what the added value of these water vapor fields can be when we want to improve the convective initiation detection. And so we have all the collection and the matchup and did some first statistical studies, and also at the same time working on the water vapor retrievals from Severi and from the flexible combined imager, for which I did not show any technical details because of the time constraint. So for the outlook is that I want to double the cases that I have now. So that can be done by including 2 years for Olgi, because we also now have a second Sentinel-3 satellites. So this is actually, we have 2 overpasses each day. And then, of course, very important, find more sophisticated or refine the descriptors of water vapor variability, and also finding a good method for convective initiation detection. So for this, for example, I can look into the nowcasting Ceph products. And then the idea is at some point to merge probability fields with the QPN fields from Ricardo. Okay, and then finally, also for the water vapor retrievals from the flexible combined imager. So we've seen that I have not showed, but the evaluation of the Severi water vapor field somehow complicated by the limitation of the cloud mass. So we're switching to a new version of cloud products for Severi, the class version 2. And then we're applying the retrieval framework to these simulation data for MTG FCI. Okay, thanks.
Thank you, Cintia, for the talk.
Yeah. Mm-hmm.
There is one question, but okay, I'll read it. From Juliano Fink. Great talk, Cynthia. What are the stations in Brazil you are validating the water vapor field? It seems they are rather few. Do you get the data from INMET?
From Brazil?
Are you related with INMET?
No.
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 Yeah.
No.
Probably he got the wrong impression or something. It's talking about the stations in Brazil, but of course, that's not the case.
Okay.
Yeah. So there's no more questions from the Slido. Perhaps we should also keep on moving.
Yeah. Let's do that. We're already pretty late.